Okay, so today we're going to talk about colligative properties, and a colligative property is a property that does not depend on what you put into a solution. It just depends on the amount that you put in. There are 4 colligative properties, and they are vapor pressure lowering, boiling point elevation, freezing point depression, and the concept of osmotic pressure, and we will talk about that in just a minute. Now, we need to discuss vapor pressure lowering, but before we discuss vapor pressure lowering, let's take a trip down memory lane and talk about vapor pressure. Vapor pressure is formed in a closed container when a liquid evaporates at the surface. The liquid particles become gas particles, and those gas particles move as gas particles do in random straight line formation, and when those gas particles hit the surface of a liquid, they create a pressure. That is called vapor pressure. So you know that if a liquid is very volatile, it will have a very high vapor pressure. A lot of the particles will go into the vapor state. All right, so a colligative property depends on the vapor pressure lowering is a colligative property, and what happens when vapor pressure is lowered is we are going to introduce into the pure solvent. Here's the pure solvent right here. Move in there. And this would be the vapor pressure of the pure solvent. Now we're going to add a non-volatile solute. Non-volatile means that the solute will not evaporate. The only thing that's evaporating is the solvent. You can see that the addition of a non-volatile solute to the solvent actually blocks the way for the solvent particles to vaporize. Therefore, when you add a non-volatile solute to a pure solvent, the vapor pressure is lowered. Look, you can see lots of little dots, fewer little dots. Everybody good there?
So there's still the same amount of solvent?
There is still the same amount of solvent. What you've changed is the addition of the non-volatile solute. Now, when we look at this, this is a vapor pressure curve. So we're looking at, this would be the equilibrium between, at this point right here, it would be between the liquid state and the gas state. And this would be the pure vapor pressure. Now, the solution vapor pressure, remember a solution would be the non-volatile solute plus a solvent, always has a lower vapor pressure. This is expressed mathematically using Raoult's law. Raoult is a French guy we looked up, and he is from the northern part of France. I thought he was Spanish. Raoult's law states that the vapor pressure of a solution is equal to the mole fraction of the solvent. This is something that you should probably star on your paper, because this is different than what we've talked about so far. The mole pressure, the mole fraction of the solvent is equal to the moles of the solvent divided by the moles of the solution. So the vapor pressure of the solution is different than the vapor pressure of the solvent when you multiply the mole fraction of the solvent times the vapor pressure of the pure solvent. So if we were talking about a non-volatile solute like salt added to a solvent water, depending on how much salt you added, it would lower the vapor pressure of the solvent water. Okay. Now, one of the things that this depends on is what happens to the solute in the water. Let's say that we have a glucose molecule, and it is our solute, and we add it to water, when we add sugar to water, it dissolves, correct?
Yeah.
Okay. And what happens, we'll use this to be water molecules. Surround the entire molecule. The molecule doesn't break up into a bunch of C's, a bunch of H's, and a bunch of O's. It hangs together, and the water molecules completely surround it. On the other hand, if we add NaCl to water, it immediately breaks down into its ions, and the water particles will surround the ions, and that's how it forms a solution. So far, so good? 1 mole of C6H12O6 will not block as many solvent particles as 1 mole of NaCl, because the NaCl breaks into twice as many pieces. Got that part?
Wait, so why doesn't the glucose break apart?
Glucose does not break into ions. It's a not electrolyte. It does not ionize in water.
Right. And it's like NaCl is ionic because they're on
Right.
opposite
So you're thinking all non-electrolytes have a Van Hoff factor of 1.
Okay.
Non-electrolytes have a Van Hoff factor of 1. Non-electrolytes have a Van Hoff factor to the number of ions they break apart into. So if I had this, sodium phosphate breaks apart into 3 sodium ions and 1 phosphate ion for a Van Hoff factor of 4. The Van Hoff factor for this would be 3. Good. Okay. Now, yesterday we talked about the enthalpy, or the energy changes when a solution was formed. And we talked about delta H1 was the expansion of the solute. And we said that was always endothermic. We talked about delta H2, which was the expansion of solvent, and it is always endo. And then we had delta H3, which is the heat that's either given off or taken in when the solution is formed. An ideal solution is one that obeys Raoult's law. This is Raoult's law. An ideal solution is one where the delta H of solution, that would be the sum of delta H1, delta H2, and delta H3, is close to 0. When delta H of solution is close to 0, that means that the solute and the solvent are very similar, that like equals like kind of thing. All right. A non-ideal solution is one that does not obey Raoult's law. Okay. Let's say you used Raoult's law and you calculated a vapor pressure of 23.4 torr for the solution. And then let's say you actually measured the vapor pressure of that solution and found that it was 24.6 torr. This is not an ideal solution because the calculated and the measured are not the same. Got that part? This is a positive deviation from the law. That means that the measured is greater than the calculated. The vapor pressure measured is higher. If the vapor pressure is higher, that means more particles are evaporating. That means that the solute and the solvent really didn't like each other very much, and they're the solvent is leaving to the gas phase. If, on the other hand, you calculated a vapor pressure of 23.4 torr and they measured the vapor pressure of a solution at 22.3 torr, that would be a negative deviation. That means in actuality fewer molecules are vaporizing. That means that the solvent and the solute like each other and there's strong interaction. They're staying put in the liquid phase. They're
So-
not leaving.
Torr is the measurement of vapor pressure?
No, that's a good question. Vapor pressure can be measured in any unit of pressure you would like.
Oh, that's not good. So
No.
ATMs, millimeters of
Mercury,
and torr.
pascals, kilopascals, inches of mercury, all the dumb,
And these are the people that want us to use metrics, but they
well,
can't unify other expressions.
no, they actually aren't the people who want us to, but whatever. I like going with ATM myself. How about you? I like that one.
I think
instead
having
of
two.
Pascals are kind of silly. Okay, and actually, that's the SI unit for, kilopascals, the SI unit for. Okay, here we go. Here is a practice problem for you. Calculate the expected vapor pressure at 25 degrees C for a solution prepared by dissolving 158 grams of common table sugar, sucrose, with a molar mass of 342.3 grams per mole, in 643.5 centimeter cubes of water. At 25 degrees C, the density of water is 0.9971 grams per cm cubed, and the vapor pressure is 23.76 torr. Raoult's law will tell us that the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. What is the solvent here?
Water.
Water is the solvent and the solute is sugar, and the sugar is non-volatile. So we're ready to go. All right, the vapor pressure of the solution is our unknown. The vapor pressure of the pure at that temperature is equal to 23.76 torr. I guess we need to know the mole fraction of the solvent. The mole fraction of the solvent would be the moles of the solvent over the moles of the solvent plus a solute, which is the solution. So I need to figure out the moles of the solvent and the moles of the solute so I can add them together. Let's do the easy part first. The moles of sucrose, which is the solute, equal to 158 grams of sucrose. The molar mass is 342.3 grams per 1 mole. That means I have 0.4616 moles of my solute. Now I need to know the number of moles of my water. First I need to find the mass of water. I know that density is equal to mass over volume. I know that the density at that temperature is 0.9971. And so I'm looking for the mass when the volume is 643.5 cubic centimeters. I didn't do that math. I skipped a step. Could somebody tell me what that is? 641.6 grams of water. So the number of moles of water equal to 641.6 grams. 18 grams in 1 mole. And I have 35.63. Yep, 35.6 moles of water. So my mole fraction is going to be 35.6 over the sum of 35.6 plus 0.4616. Excuse me. My mole fraction is 0.9873. I'm finally ready to solve this problem. X is equal to 0.9873 times the vapor pressure of the pure, and I'm hoping that is equal to this.
There's quite a few more moles of H2O.
Yes, there are. Yep. And there were, in these problems, the mole fraction of the solvent will be over, generally over 0.5, because usually there's more solvent than there is solute. Okay, now this one is different because this we had a molecular solid, which means it only broke up into, it did not break up. Now we're going to talk about an ionic solute, and it will break up. So, predict the vapor pressure of a solution prepared by mixing 35 grams of solid Na2SO4 with 175 grams of water at 25 degrees C. The vapor pressure of pure water at 25 degrees C is still 2376. So, the vapor pressure of the solution is equal to the mole fraction of the solvent, which in this case is water, times the vapor pressure of the pure. The vapor pressure of the pure, 23.76 torr. The mole fraction of the solvent has to do with the number of moles of water equal to 175 grams, 18 grams per 1 mole, and we have 9.72 moles of water. All right. Now the number of moles of sodium sulfate equal to 35 grams. 1 mole of sodium sulfate is 142 grams. And that means we have 0.246 moles of sodium sulfate. However, this is tricky because sodium sulfate, when put into water, breaks into 3 pieces, doesn't have a Van Hoff factor of 3. So you have to multiply this by 3. If you had 1 mole of sodium sulfate, it would produce 3 moles of ions. Everybody agree with that? Mm-hmm. And so what it would look like in solution with the water particles would be surrounding the ions.
So would it be Na, and SO4? Or?
Mm-hmm. Just like this. All right, so the number of moles of ions that are blocking the surface and preventing the solvent from evaporating is 0.738. So the mole fraction of the solvent is 9.72 over the quantity 9.72 plus 0.738 is equal to 9.929? Is that what y'all got?
Yeah.
Okay. So here's some math, 0.929 times 23.76 is equal to this. Now, what you should be on the lookout when you do these problems is whether your non-volatile solute breaks up into ions or stays together, because it's going to determine a different answer for you. Oh, he's back and on camera again today. 2 times.
Nick Hoffman.
Don't say his name out loud. I have to give credit for it. Don't get in front of the camera either. There we go. Thank you. That's
You can just leave
close.
that out.
All righty. Okay.
Me?
All right, ladies and gentlemen, we are going to be finding the molecular mass of a solute by using the vapor pressure. We're going to be doing something similar to this in the lab. Actually, if we look at this really quick, using Raoult's law, you can solve for the mole fraction. You know how many moles of solvent that you have. You figure out how many moles of solute you have. And if you know the amount of the solute you started with, you figured out how many moles by figuring out the vapor pressure of the pure and the vapor pressure of the solution, you can find the molar mass. Yay. All right, now, what happens when your solute and your solvent are both volatile? In that case, what's happening is, here's my picture. What would be happening is then also you would have the solute contributing to the vapor pressure. So the vapor pressure on the surface would be a combination of the solvent and the solute. So you'd have to account for that mathematically. And this is the math that you would use. The vapor pressure of the solution is equal to the vapor pressure of the solute plus the vapor pressure of the solvent. Well, that didn't take a genius, now did it? So you just add these two together. A solution is prepared by mixing 5.86 grams of acetone and 11.9 grams of chloroform. At 35 degrees C, the solution has a total vapor pressure of 260 torr. Is this an ideal solution? So this is the measured VP of the solution. They're asking us to figure out what the calculated VP of the solution is and see if they're equal or not. In order to do that, we have to find the vapor pressure of the solute, and then we have to find the vapor pressure of the solvent. Just by looking at this, which one's a solute and which one's a solvent?
Acetone's a
Acetone.
solute.
Yep,
Solvent is-
acetone's a solute and chloroform is a solvent.
That was a guess. How do you
This
more-
is a smaller quantity than this.
Oh,
Okay, so let's think about these as two separate problems and then add stuff together at the end. So I want to find the vapor pressure of acetone, and that would be the pressure of that solution of acetone is equal to the mole fraction of the acetone times the pure. So the mole fraction of the acetone, I'm going to need to know the number of moles of acetone. And that would be 5.81 grams times its molar mass, which is 58.1, which is 0.1 mole. The number of moles of chloroform, HCCI3, equal to 11.9 grams, and its molar mass is 119 point something, 4, is also 0.1 mole. So the mole fraction of the acetone is equal to 0.1 over 0.2, get it? Which is 0.5. What's the mole fraction of the chloroform then? Yep, 0.5, because the two mole fractions have to add up to 1, so it's 0.5 as well. All right, so my vapor pressure of the acetone is equal to its mole fraction, 0.5, times its pure vapor pressure, which is 345. And that's 170 something. What is that?
172.
Point what?
5.
Okay, so we'll call it 173 torr. And then the vapor pressure of the chloroform is equal to its mole fraction, which is 0.5, times its pure, which is 293. So that is about 140 something. What is that? 147 torr. So together, the vapor pressure of this solution is that. Is that correct?
320.
Yeah, okay. So this is the calculated vapor pressure, and the measured vapor pressure is 260. Is this a positive or a negative deviation from Raoult's law? It is negative. That means not as much of the solvent has evaporated as we thought it was going to. Does that mean that there are strong solute solvent or weak solute solvent attractions? Strong. Okay, that's all I got.
We switch them over.